Hello, I'm Behzad Bojnordi Arbab, and today I want to talk about unveiling the structure of evolved stars' extended atmospheres, the capabilities of SK and ngVLA for the future. I'm a doctoral student at Chalmers University of Technology, and my collaborators here are Wouter Flemings and Theo Khoury from Chalmers University of Technology and Susan Höfner from Uppsala University. The objects in discussion for me here are the asymptotic giant branch stars, or AGB stars. It refers to the stage in life cycle of a star when it has exhausted the hydrogen fuel in its core and starts fusing helium. This leads to a significant increase in size and luminosity, making the star appear as a red giant. These stars are very large. They are about 200 to 500 solar radius, which translates to 1 to 2.5 astronomical unit. In this phase, the star undergoes intense pulsations, which drives changes in the star's temperature and luminosity. These pulsations can cause the star to vary in brightness over the timescales of approximately 1 year. The internal structure of these AGB stars is very complex. It's a helium burning shell surrounding an inert carbon oxygen core. And outside this, it's a helium shell. A hydrogen burning, also outside of this helium shell, a hydrogen burning shell exists. And the outer layer also consists of very large convective cells that drive large scale changes to the surface of the star. On the other side, you can see a schematic model for a neighbor AGB star named W Hydra, based on the early radio observations. You can see the atmosphere and how it has shaped the outside of the star. On the left, you can see a model showing the structure mostly out of the stellar atmosphere. Take note that this model is not in scale, not even logarithmically. The pulsations from the star surface, shown bright red here, introduces shocks to the dynamical or extended atmosphere where dust formation happens. In the outer regions, there is a circumstellar envelope where a stable outflow exists that reaches further and enriches the interstellar medium. The important thing here is the mass loss for us. The current models explain that the dust shaped in the extended atmosphere is affected by the radiation pressure from the star and therefore accelerates radially outward. This dust also pulls on the existing gas around it and produces a wind that brings the gas to the outer layers and drives mass outward from the star. So what is the big role of the AGB stars that makes them special? Here you can see a periodic table of elements showing their origins. Everything green here is from AGB stars. So AGB stars are primary source of carbon, nitrogen, and other heavy elements in the universe, which are essential building blocks for life. The heavy mass loss during the AGB phase also shapes the interstellar medium and produces planetary nebulae. Mass loss also plays an important role in shaping the structure of these galaxies and chemical evolution of the universe as a whole. The amount of mass loss and the initial mass of the star also sets limits on the later evolutionary stages of the star itself. There are many things that we don't know about AGB stars and the mass loss mechanism. For example, the stellar hydrodynamical models work pretty well before the AGB phase, but as in this phase, the stellar mass changes considerably, and a large portion of the star is variable. The models are not well constrained, and empirical methods are still in use. The dust-driven wind model does not produce enough mass loss in high mass AGB stars. We have this problem here. And also there is a dust formation issue. We know that inside the star, it's not suitable for dust to form or exist. On the outside of the extended atmosphere, we can detect an abundance of dust. As a result, the dust content should be produced in this layer. But what are the conditions? What are the variations and important factors for the dust formation region? And also, how can we relate the star properties before the AGB phase with the mass loss rate of the star? In order to see this, we use some star-in-a-box models. They simulate star in a whole, as a whole, but can be specialized with different regions and purposes. These are hydrodynamical models with radiative and convective energy transfer. We can also see short-term variations and also long-term variations in these models. These are two models. One is Darwin, a one-dimensional simulation that includes radial variations, and it's lower in cost, so we can have many more models, and it goes to much larger radii. And on the other hand, we have Cobalt, which is a three-dimensional simulation. It's much more costly. We have much less data points for that, but it also includes asymmetries and shape changes of these stars. In order to review the capabilities of the best current ALMA and VLA for AGB stars, we take a look at the resolution and sensitivity potentials of these instruments. In this figure, the angular resolution versus frequency of the array is plotted using Darwin models and also various power law models for density, temperature, ionization, and also ionization profiles for the extended atmospheres of a test AGB star. We produce synthetic images, and assuming different distances for the objects, we can measure the radius of these stars. The blue regions here, which are labeled with each distance, show the extent of these radius for various models as a function of frequency. Based on the comparison with the resolving capabilities of the instruments shown here, VLA lower bands are not suitable for resolving these stars, but higher frequency bands can resolve the nearest AGB atmospheres. On the other hand, ALMA is looking at higher frequencies and as a result can observe AGB stars up to a couple of hundred parsecs. These instruments enable us for the first observations of AGB stars in the current decades. There have been observations in recent years in millimeter, submillimeter, and infrared wavelengths. Interferometry arrays are used to produce images of these nearest AGB stars, such as W Hydra, Myra A, or Doradus, and also the supergiant Betelgeuse. I included Betelgeuse here because it is the largest visible star in angular diameter. So this is the best that we can currently do in these frequencies. I wanted also to add that if you want to hear more about evolved stars from a true expert on high resolution observations of these stars, tune in for Wednesday talk by Lynn Matthews in this field. To show these observations better in context, here you can see some of the recent observations compared with the current capabilities. For example, W Hydra was barely resolved with VLA, but with ALMA band 7, we can resolve the star much better. It's worth noting that the different frequencies tell us different stories about the atmosphere of these stars, which I will talk more about it in the next slides. We saw that the current capabilities. Now let's see what the future instruments bring. First, I want to show you the capabilities for unresolved observations. In this plot, you can see the flux density versus image noise levels of these instruments. We can observe objects that are higher than the level of instrument noise levels shown here. As you can see, ALMA can theoretically observe up to 10 kiloparsecs, but unresolved dust emissions pollute it. This problem is less serious in VLA frequencies, so we can expect observations for about 2 kiloparsecs. When SK is available, we are introduced to higher sensitivities. As you can see here, the bands lower than 1 gigahertz are also available for these stars. And we can observe faster because SK is a better sensitivity and the field of view. But when ngVLA comes to the scene, it will bring the available theoretical distances to even extra galactic regions. If ngVLA was in the southern hemisphere, we could observe Magellanic Cloud AGB stars in these frequencies. Now let's go for the more exciting resolved observations. As we saw earlier, ALMA and VLA have the ability to resolve the nearest AGB stars. But SKA can bring the ability of ALMA in resolving the AGB stars to much lower frequencies. As a result, if we use both arrays together, we can observe in our neighborhood AGBs from 5 gigahertz to more than 1 terahertz by using ALMA and SKA together. This enables wide multi-wavelength observations of the AGB atmospheres, which is very important. I will talk about it more here. ngVLA, when it comes to the scene, it changes everything. We can resolve almost any AGB star visible in our galaxy. It also lets us bring the multi-wavelength observations to even lower frequencies. Remember that ngVLA was also capable in sensitivity for such distant objects. Here, the lower bands will struggle more in sensitivity rather than in resolutions. As I said, the multi-wavelength observations are very important here, and I want to explain why. As you can see here, we show one atmospheric model. On the left, we see that the radius of the star changes considerably with frequency. The free opacity is the dominant source, and it is higher. This opacity is higher in lower frequencies. So the outer parts of the star are opaque in lower bands, while they are transparent in higher frequencies. In other words, observations in different frequencies show us different layers of these atmospheres. If you want to go deep, use higher bands. Also, we look at higher frequencies. We observe inner hotter regions, so the brightness temperature increases. This is shown on the right panel. Here, various power law models are shown, which show the extent of possible radius and brightness temperature profiles. As you can see in both panels, in high frequencies, which correspond to ALMA bands, the differences between the models are much less than in lower bands. As a result, low frequency observations are invaluable in constraining the models and atmosphere profile patterns. One of the most important properties of these stars is variability. And we know that SKA and ngVLA make it possible to measure flux densities for a large set of objects. Here, we see the flux density variability of an unresolved AGB star model in different bands. These are the current available bands, and you can see that the data used here are from Darwin models, the one-dimensional Darwin models in different phases during one period. We can clearly see that there is not one simple variability for all these frequencies. Observations in some bands, for example, ALMA band 4, in this example, do not show much variability, but we can see it clearly in other bands. Also note the difference between the phases that we see the maximum. The different profiles are very helpful for constraining the stellar models. Here, the SKA data is added, and we see that we have extra data at lower frequencies, and it increases the number of observable objects by 1 order of magnitude. And when ngVLA comes into the picture, it increases the number of available objects by 1 order of magnitude again. At last, let's see how valuable are these multi-wavelength resolved observations. Here we see a Darwin model in different phases, virtually observed in some of the current bands, and measure the radius for each of them. We add SKA to see that the lower frequencies, for example, the blue SKA 5 gigahertz, there is a peak in radius about 400 gigahertz. But you can see that here we see a minimum for ALMA band 9, the red profile. This happens for the minimum too. It means that the largest and smaller sizes of the star depends on the frequency of your instrument. It may be the largest in one band, and at the same time, the smallest size in another band. We also bring ngVLA into the picture so that we can have family all together. And from the Darwin models, we also have the density profile. So we draw the shock wave on the plot. As you can see, the shock goes outward with time. And in this model, we can see two shocks at the same time. The low frequency bands are very interesting here. As you can see, the radius increases in these bands together with the position of the shock wave. As a result, these bands may be good tracers of shock waves, and we can observe the wave directly in these bands. So we need repeated low frequency, high resolution observations for this. Here I leave you with the conclusions. We have started our first steps to study AGB stars, extended atmospheres with ALMA and VLA, but SKA and ngVLA let us explore this field like an adventure. Thank you very much for listening.
Okay, our speaker is online and available for questions if we have any. There are no questions. Oh, there's one.
Hi, thanks. This was very interesting. I was wondering, so you didn't mention LOFA at all, basically, or maybe I missed it. Is a spatial resolution not good enough to include it? Because I mean, you would then go again like an order of magnitude lower in frequencies.
Actually, yes. The resolution required for this purpose is not enough. Also, SKA low is not good for this purpose. Yeah.
And LOFA 2.0, would this be something?
I haven't checked that.
Okay.
Yeah, I don't know. Maybe.
Are there any other questions on? Oh, okay. Are there any online? No. Okay.
Thank you for the talk. Right now in star forming regions, it's really frustrating because your background AGB stars contaminate what we think are young stellar objects. And I'm just wondering whether, is this going to like just completely change that game? Is there enough diagnostic that you're just going to very quickly be able to say AGB, 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 and then we won't have your contaminants anymore?
I hope, because until now, we didn't have the resolution enough to observe these as good as we wanted. And I think because if we don't have this resolution, also the contamination from dust around it will affect this. So I hope that helps to identify AGB stars much better than before. Yeah, it's better for you and better for us both.
Sorry about that.
Yeah, I have a couple of comments in relation to that last point. So first of all, I think if you're doing stuff behind star forming regions, you may have scatter broadening that may actually make this technique not work very well. But the flip side of that is I think with proper motions, you should be able to select those out. And if you have a lot more sensitivity and the same resolution as we have now, that may be the way to get rid of your AGB stars.
Thanks.
Okay, if we have no further questions, let's thank our speaker and all of our speakers this afternoon. I also want